Greetings, this is GN112, Module 1, Review of Horizontal and Vertical Positioning. So we will start with triangulation and trilateration. So we will define these terms. We'll go to the basic principle of triangulation. And the objective of triangulation surveys. So why do we do these surveys in the first place? And we have triangulation figures and layouts. So these are the different configurations of triangulation networks. Then well-conditioned triangles. How do we define a well-conditioned triangle? So this is essential in designing a triangulation network. And then lastly, we go to strength of figure. So let's start. Triangulation is based on the trigonometric proposition that if one side and two angles of a triangle are known, the remaining sides can be computed. Okay, so we will use the sine law for computing the other sides, right? Then a triangulation system consists of a series of joined or overlapping triangles in which an occasional side is measured and the remaining sides are calculated from angles measured at the vertices of a triangle. So you will see here a figure. So the vertices here are the triangulation stations. So some triangulation stations are unoccupied, but most of them are occupied. Then we have here our baseline. Okay, the baseline is the line with a predetermined length. So that means we measured line AB. So here our baseline is line AB. Now if we measure all of the angles here for this network, then we can calculate the lengths of the other sides. Now, a trilateration system also consists of a series of joined or overlapping triangles. However, for trilateration, the lengths of all the sides of a triangle are measured and few directions or angles are measured to establish azimuth. Now, this is the main difference between trilateration and triangulation. So, for trilateration, you measure the lengths of the sides. In contrast, in triangulation, you measure the angles, right? So, before electronic distance measurement instruments, for example, the total station, so before the invention of that instrument, um, triangulation, triangulation was mainly used because it is very hard to measure long distances accurately because historically you have to use the tape, right? And there are many errors that can come when you use the tape. Okay, so after the invention of EDMs, then we can use trilateration along with triangulation. Then the principle of triangulation. So let's say we have here a base AB, and you want to know the the length of our line CD right here. So if AB, so we know the length of AB, right? So if we measure 1, 2, 3, angles 1, 2, 3 until 6, then we can calculate for um, the length of line CD. Then we have here the azimuth of line AB. So if we have the angles 1 to 6, then we can also calculate for the azimuths of all of the other lines. Okay. We move to the objective of triangulation surveys. So to establish accurate control for plane and geodetic surveys of large areas by terrestrial methods. Okay, this was discussed in the first video, in the introductory video. And then to establish accurate control for photogrammetric surveys of large areas. Okay, so in photogrammetry, we need control points because um, we use them for geometrically correcting the aerial photos, because in the aircraft there are different variables. There are your aircraft can tilt, so then you have to compensate for that. You have to correct your photos to be geometrically correct. Then to assist in the determination of size and shape of the Earth by making observations for latitude, longitude, and gravity. And lastly, to determine accurate locations of points in engineering works. Okay, for triangulation figures and layouts, so we have 5 right here: single chain of triangles, double chain of triangles, braced quadrilaterals, centered triangles and polygons, and a combination of the above systems. Now let's show some figures of these. So we have here the single chain of triangles. You can see. So if you have a check base AB, and we can calculate for HG. And the disadvantages for this is that we only have one route for computing HG or GH. So what do you mean when you say one route? So if we know AB, then you can, using sine law, you can calculate BC, right? And then you calculate again CD. So we only have one route until you reach GH. So you will see later what other routes will look like when we go to quadrilaterals. We have your double chain of triangles, so this is how it looks like. So basically, single chain of triangles or double chain of triangles are used when the survey area is quite narrow. So an example is the river. So you can use this configuration for that. And also depends, the design also depends on the accuracy that you want. And also depends on the time that you have, because if you have more stations or more observations, then definitely it will cost a lot also, and also it will take more time. Okay, for braced quadrilaterals, so this right here is arguably the strongest form. You have right here, let's see, if you have a baseline of AB, then you can calculate for, let's say, CD in four different routes. You can use BC as the common side, AD as the common side, and then you can use AC as a common side, diagonal, and then you can also use BD as a common side. So you can have checks for computing the value of CD, and then as you move forward, you have checks as well until you reach GH. Okay, we have centered triangles and polygons. So this is how it looks like. We have a triangle here, ABC, with a center point of I, center station of I. Then a pentagon, and also a quadrilateral here with a center of K. So application example, we have here the grid. It's called the gridiron. It's used in Austria, Spain, and France. So we have right here a chain of quadrilaterals, right? And then we have another application right here. This is called the central system. This is used in England. And we have here a central triangle ABC, and then you expand in all directions. Now, the gridiron is more stable compared to this central system. Now, for well-conditioned triangles, so how do we determine if our triangle is well-conditioned? Now, we know that we use the sine law, right, in computing for the other sides, given one side and the other angles. And if we take a look at the sine function, we have right here this blue line coincides with 30 degrees, and then this green line corresponds with 120 degrees. Now, if we take a look, the smaller the angle or the larger the angle as it approaches pi, um, the graph has a steeper slope, right? Compared to, let's say, from so let's compare a 0 to 30 degrees, and then 30 degrees to 90 degrees. So we can see that from 30 degrees to 90 degrees, the slope is smaller compared to from 0 to um, what do you call this, 30 degrees, right? So what does this mean? So as if your angle, when you measure the angle, so the value of the sine increases rapidly, right? So if you have an error there, then that will definitely affect the computations. So largely affect the computations, right? So in practice, the angles are maintained from 30 degrees to 120 degrees. So they will only range from 30 degrees to 120 degrees. Now you might say, why are we limited to 120 degrees? So remember that we are talking about single angles here, and we have a triangle, right? So if you have 120 degrees for one angle, and that means you only have 60 degrees left for the other two angles. And since we have a limit of 30 degrees, so we have to limit it to 120, right? 180 minus 120, that would be 60, divided by 2 is our limit, 30 degrees, okay? So that's it. So you have to limit your angles from 30 to 120. But there are also unavoidable cases where this rule is not followed, So there are also ways to compensate for that. You introduce more checks, and yeah, so that's it for how you determine well-conditioned triangles. And then we will proceed with strength of figure in the next video. So thank you for watching this video, and I hope you learned something new, and I'll see you in the next video.